Howdy, welcome to the Smart Grid Center webinar titled Modeling and Simulation for Large-Scale EV Integration Studies, ElectroTempo and Texas A&M Joint Projects. I'm Andrea Kishne from the Smart Grid Center. First, let me ask you to send questions in the Q&A window anytime to get those addressed, mostly in the end of the presentation, except some clarifying questions if it is needed. Or raise your hand with the hand button in the Zoom window, and I will allow you to unmute yourself and ask questions or share your comments after the talk. The presenters today are Dr. Jonathan Snodgrass and Dr. Ann Shu. Jonathan Snodgrass is a research engineer at Texas A&M University, working under Professor Tom Overby in the area of large-scale electric power systems. He received his bachelor and master's degrees at Texas A&M University and master's and PhD degrees at University of Wisconsin-Madison, all in electrical engineering. His primary research area is in power system, network planning, and resilience, with current projects focusing on light, medium, and heavy-duty EV integration using combined transmission and distribution core simulation. His other research areas include modeling impact of high-impact, low-frequency events such as geomagnetic and electromagnetic pulse disturbance on the electric grids, power system optimization, and microgrids. He also worked for 2 years at Zachry Engineering Corporation in Amarillo, Texas, designing simple and combined cycle natural gas generating plants. Dr. Ann Shu is a co-founder and CEO of ElectroTempo, that is a software-as-a-service company creating solutions for EV charging, infrastructure planning, and intelligence for electric utilities, charging site hosts, and fleets. Dr. Shu spun out of ElectroTempo from TTI, Texas A&M Transportation Institute, where she led the research and development of large-scale regional electric vehicle charging demand simulators. Prior to TTI, Dr. Shu was Senior Technical Advisor for Impact and Assessment at DOE ARPA-E. Dr. Shu received her PhD in Transportation Systems Engineering from Georgia Tech, where she conducted extensive research in transportation and energy. Dr. Snodgrass and Dr. Shu, take it away.
Sounds great. Awesome. Well, we'll pass off the presentation a couple of slides in. So I'll launch off. Howdy, everybody. As we mentioned, I'm Jonathan, Dr. Snodgrass, and Dr. Ann Shu is here as well. So we'll be focusing on joint projects, collaboration between ElectroTempo, a startup that Ann has founded a couple of years ago, and Texas A&M University. And so Mike and Ben are a few of the people on Ann's team. And the primary team here at Texas A&M University is myself, I'm Professor Tom Overby, and then 3 graduate students. I'm Diana, Nicole, and master's student Lyric. So 2 PhD students and a master's student, although we have plenty of people assisting with the research from undergraduate research perspective and other collaborators as well here today, and other students helping out. So kind of as a bit of background and motivation for electric vehicles, the discussion about EVs would not be complete without a discussion about renewables. And as most of y'all know, the duck curve has been discussed for many years now. And I just pulled this duck curve. They don't have the data for 2024 yet. But if you've noticed, in 2023, the net load at some points was actually negative, meaning that California had a net export of solar during the day. And this poses increasing challenges as you consider EV integration, because if people show up from work between 6 and 8 p.m., that makes this peak even higher when people plug in their electric vehicles to charge upon arriving home from work. And looking at the ERCOT combined wind and solar, thankfully it's not as severe at ERCOT because, to quote one of our collaborators at ERCOT, when God designed Texas, he put the wind out in West Texas and the sun all over the state, and he made the wind blow at night and the sun shine during the day. But the problem is, end of quote. And the problem is, though, you have this dead time me see if I can find a better, here you go, much better. There's this low point where you have the solar roll off, especially when there is when the days get shorter, or if it's cloudy. You have this solar roll off into the evening, and then you have the wind might be slow to pick up. So there was one day last summer where the solar was dropping off and the wind was slower to pick up than forecast, and we wound up with some tight margins on the system. But again, if you look at, you know, this is today's forecast. So it's today we're looking great. But some days you wind up with the purple line being the combined wind and solar. You wind up with this dip right here winding up between, you know, 5 and 7 p.m. where you have this dip because the solar is rolling off and the wind hasn't yet picked up. So that might raise the question, how does this relate to electric vehicles? So first thing I'm going to do is kind of motivate our research and our projects by asking the age-old question, asset or liability. And so there's electric vehicles, like pretty much everything in the power area, is gathering a lot of national attention. It can be and is unfortunately highly politicized, and people say one thing or another about electric vehicles and about the grid itself. But the question is, what is kind of the truth behind whether it's a liability or an asset? And the answer is it can be both. So if you have, as I just mentioned with the showing those two renewable curves, is that if you have uncoordinated charging, you can wind up adding to the peak load between, you know, 5 and 7 or 8, 9, 10 p.m., making an already stressed system worse. Also, too, if you have an L2 charger, if you say install an L2 charger in your garage, if it's a 50 amp circuit at 240 volts, that about doubles the energy usage of your house. So we were looking at some forecasts. I know this is California, but California has the highest EV adoption rates by far of any state. And for 100% EV adoption, we're looking at scenarios where that would more than double the PG&E load. So that's not an insignificant amount of energy or power too. And there's also, but specifically here for Texas, there's a lot of uncertainty about future EV adoption rates. There's scenarios that range from only a few handful of a percent to 50, 75+%. And so it's very hard for utilities, grid coordinators, ISOs, PUCs to be able to really get a handle on what the EV load might do in the future. But the EVs can also be viewed as a grid asset or used as an asset to the grid. In addition to their primary goal of moving people and goods, electric vehicles can be viewed, modeled as a energy demand with power constraints. And I'll get into that a bit more in the future, but kind of put that in your mind of an EV is both an energy load and a power load. In the sense of compared to an AC, you know, when it's hot outside, you want your AC on, you want it at full blast. Whereas an electric vehicle, if you plug in at 6 or 7, maybe later for some of y'all, when you get home from work, you know, you don't, as long as, you know, you're done for the day, if you've run your errands, you picked up your kids, you know, you're home for the night, you don't particularly care exactly when your EV charges. You just care that in the morning it's got enough juice to go to work, to run your errands, drop off your kids, go to the soccer game, or go to the Aggie football game, being a Mags. But the point is that there's some flexibility, and there's a lot of talk about vehicle to grid. This talk is not going to get into that because it's kind of our viewpoint that we can achieve the vast majority of the benefits of EV flexibility just using grid to vehicle and not pulling power out of someone's battery to try to support the grid. But the point is that it's a flexible demand. So if you have price signals from the grid, you have managed EV charging, coordinated charging, you can wind up you can shift that EV demand to when either renewables are higher or it's kind of off peak from the peak evening demand. Subject to energy constraints or power constraints, you can only charge so fast. Subject to energy constraints of you want your car to be charged by morning. And also grid support as well. So we're not going to get into the frequency support. There's a host of challenges with that. But at the very least, you can modulate EV charging. Some chargers allow you to be able to change the rate of charge. And so you could then, instead of saying, oh, everyone stop charging, you could back off charging, or you could even modulate it within some range to be able to account for fluctuations in renewable energy output, small fluctuations. That's another potential opportunity for electric vehicles. pose a couple challenges real fast, and then we'll pass over to Anne. So if you're a power systems person, you have seen this graph before. This is the classic time scale separation. So showing that we can have a whole variety of people, and we probably have people spanning this entire time scale separation on this call. You've got people who do research in power electronics, and so that's on the order of microseconds. So high frequency switching devices, inverters. You've got relays all the way up to T&D planning, which is on the order of a decade, and everything in between. And there are probably people on this call that are in charge of the entire, that cover this entire spectrum. The difference, though, is that what you see these different peaks that have some overlap. What you don't see, and I didn't plot it because it covered the entire graph, is electric vehicles cover this entire spectrum. So they're connected with, obviously they're connected with AC to DC rectifiers. So they have switching transients that sometimes get modeled, sometimes don't. They can, with a lot of finesse, operate on the millisecond time frame to be able to provide frequency support. That hasn't been commercialized yet, but there is the possibility. There's definitely the system dynamic response. If you have a lot of EV chargers switching in around the same time, it will affect the grid dynamics. EV charging can be used to track wind and solar outputs, variation on the order of seconds to hours. And then and it's also part of planning. I mean, if you're going to, is someone not, okay, someone says we can't see the slides. Okay. Looks like Zoom has stopped working. Give me 1 second, y'all. Okay. It wouldn't be a good presentation without a technology challenge. Okay. Can someone come off mute and answer, or Andrea, what was the last slide you saw?
I actually saw your slide. Okay.
Okay. Great. Okay. So it might have just been something on Andrea's side. Perfect. Okay, good. Back to the awesome. Thanks. Back to our regularly scheduled presentation. Where's my, I'm going to annotate. There we go. So it also goes into the T&D planning perspective. So if you're going to, for example, looking at a study we're doing for PG&E, if you're going to have high adoption of EV on your distribution system, you might wind up having to substantially upgrade distribution lines, install new transformers. So you're going to get into the years to potentially decade, especially if you need to reconduct your transmission lines. So EV simulation and integration covers this entire timescale separation. And so it's very difficult because traditionally we've siloed things in power systems, and for better or for worse. We have our transmission, our planning, our operations, our day ahead, our distribution system. We have our power electronics people. We have our relay protection control, and they all operate differently. The problem with EV is you have to know a little bit about everything to really be able to do good and accurate analysis, which is a bit of a stealing the thunder. That's what we've done with ElectroTempo. So we have here at A&M, we have people that cover this entire timescale separation, all the way from Dr. Bailog's power electronics research to Dr. Overby's T&D planning to everywhere in between, distribution, et cetera. I see somebody's hand raised. Do you have a clarifying question? Jeremiah has his hand raised. If you can just type your question in the Q&A, that would be great, just so I can keep on going. And then a couple of last points on the challenges is that, as I just mentioned, a lot of some utilities and ISOs don't have a specific department or team that does EV modeling and integration, just for the reasons that I mentioned. It's different. It spans these timescale separation, and it's fairly new. I mean, compared to traditional power system analysis, it's fairly recent. The second, but so as I mentioned, in collaboration with A&M, ElectroTempo and A&M, our collaboration enables us to do this high fidelity modeling and simulation. Jeremiah, I see you. If you have a clarifying question, go ahead. Negative. Okay, I'll keep going. So the other difficulty is that traditionally there aren't a lot of good scenarios, distribution, transmission, and transportation models, data sets, and scenarios for EV growth and adoption. If you look at the literature or reports, there's a lot of research done in this area, but it's either, and I mentioned this in our previous webinar, so feel free to watch the recording a little bit or check out the slides. There's a lot of simplification, oversimplification on either the transportation side, the grid side, or both. And I can go into more detail during the Q&A. I can go into more detail in the Q&A if anyone has more questions there. But again, our joint partnership has worked to overcome this. So this is the perfect segue to Dr. Shu's slides, where she will present the detailed modeling that ElectroTempo has done on the transportation and EV side. And then for the last 10 or so minutes, I will discuss more detail about the A&M's grid modeling side of things, and we'll leave some time for Q&A. So Dr. Shu, please take it away.
All right, thank you so much, Jonathan. Hi, everyone. So good to see you again. Hopefully, if you joined our joint webinar before back in May. If you have not, I do have a few slides back from May, just as a quick refresher, because most people know who A&M is, but you probably don't know who ElectroTempo is. So please allow me just a couple minutes to introduce ourselves to you. So we're a software company focused on EV charging infrastructure planning and intelligence. And by that, we really mean two things. One, and foundationally, our software estimates EV charging demand. So demand forecasting is the very step of infrastructure planning and operations. And then the other side of it is that we help with infrastructure optimization. So naturally, we actually have a lot of customers in the utility space, but we also have customers in commercial real estate and fleets who are looking to put in chargers to support support electric vehicles. I wanted to introduce my leadership team. So myself come from the transportation side. As Andrea introduced in the beginning, I have my PhD in transportation systems engineering, and my entire career's research has been in transportation and energy modeling. And it was because of my research that I was recruited to ARPA-E, the venture arm of DOE, where I actually had the fortune of overseeing a $15 million program called Transnet, which was focused on using software and simulation to identify energy efficiency opportunities in the transportation system. It was at ARPA-E that I met my co-founder and CEO, Patrick Finch. So Patrick brings to the table extensive experience working in the energy space, working with commercial real estate and utility partners. So together, we bring both sides of the perspectives. And more recently, we added our CTO, Sean Mohanthan, who has brought with him extensive experiences in software development. But we also made sure that his software development experience was deeply rooted in the transportation space, so that we can make sure to create a solution that is based in subject matter expertise in the transportation and energy space. So Jonathan's been talking a lot about our collaborations. So let me get down to the details and introduce the two specific DOE-funded projects that we've been working on. There are a lot more that are on the horizon, but these two, we've made great progress. And I'm going to go into details on both of these. So on the left side is called Scalable Truck Charging Demand Simulation for Cost-Optimized Infrastructure Planning. This project has been going on for almost 3 years now. It's about to come to conclusion. So we have some great results to share, and Jonathan shared a lot of those during the May webinar. It's focused on truck charging. The other project is actually focused on passenger vehicle charging. It is called a utility scaled plan for accelerating deployment for multifamily EV charging infrastructure. This project is bigger than the first one, so our collaboration has expanded and deepened. This project is about midway. It is I feel very excited to be sharing these projects with you because they really represent two very diverse vehicle segments, but also two very different geographic areas. The first project is focused on Texas. Specifically, we were looking at the I-45 corridor between Houston and Dallas as a case study. And the second project is focused in California, specifically the PG&E territory, so in Northern California. So let me keep going so you can see in more detail about these projects. I wanted to tie the two projects together, though, with a fundamental problem statement. That is that charging infrastructure must meet demand. It may be, self-evident on the surface, but the challenge here is that with EVs, the demand is twofold. So we have, so it has to, when one think of demand, we're bringing together two very different sectors, the transportation sector and the electric sector. The think of demand, like demand, the word demand itself actually means different things to the professionals in the two sectors. So let me clarify here. Jonathan talked a lot about the potential for EVs to be as grid assets, the flexibility it may provide. But we wanted also to clarify and deepen that statement and that view with a perspective coming from the transportation side that's rooted in the realities of transportation. That is, the EVs are first and foremost a mode of transportation. And therefore, the extent to which EVs can serve as grid assets have to be understood based on travel demand. So how much people travel, how much goods travel, where and when, what are the origins and what are the destinations. And that really was what motivated our collaboration from the very beginning. So ElectroTempo, us coming originally from the transportation side of things, we bring our understanding, the data sets and the simulations, the mechanisms on the transportation side, such that we can identify potential high charging demand, so charge energy and power requirements from fleets, from transportation corridors, and from areas where density is high, such as multifamily housing or workplace charging. So let me break down that problem statement into the two projects, starting with truck charging. So this project, again, funded by DOE, we have, it was a 3-year project broken down into 3 distinct tasks. The first year was mostly focused on translating travel demand, so truck traffic patterns and origin and destinations, into how much trucks are likely to charge when trucks do transition to electric. So for us to do that on the transportation side, we actually broke down truck operations into 2 distinct segments. One is local and mostly urban truck operations, and the other is long-haul truck charging. So we break our simulations into these two segments really to provide more realism and fidelity into the simulation, because that's because these local operations, just from a transportation perspective, local operations have very different patterns compared to long haul operations. So that these two actually correspond to two very small, just two very small boxes here. So urban truck charging right here and long haul truck charging right here. And during the May presentation, Jonathan already covered all the results in the cost optimization part, so task 2. So I won't repeat that part. Back to truck operations, how we simulate charging demand. So for local truck operations, we consider a host of different data sets. So first and foremost, truck depot locations. Where are the depots? Where do trucks spend most of their time that can be a prime location for charging? And then the trips, the origins and destinations, the duty cycles, meaning how fast these trucks travel, how far they travel, how much, stop and go situations they experience. Those all affect the energy consumption rates. And so it also includes weather patterns, hotter or colder. And these we take all of these factors into consideration as we estimate how much energy is required for a truck to fulfill its daily operations. And then, of course, arrival patterns at each location. On the long haul side, we consider national freight flows, because now the spatial scale is different, right? It's more about commodity flows, origins and destinations, the routes the trucks take to move these commodities, and the parking locations along the way. Believe it or not, every single point that I just now listed actually have very scarce data. So traditionally, trucking information is hard to obtain. But today, even with telematics information, there's typically a lot of gaps in existing data. So for us to localize truck charging, meaning to really pinpoint where truck charging is likely to occur, which is very important in grid planning and operations. That actually requires new data sources. And this I wanted to kind of just add to Jonathan's point about our collaboration. It is this cross-disciplinary collaboration between us and the Smart Grid Center that allowed us to understand some of the fundamental differences in understanding traffic patterns. So, for example, whether or not, a truck depot, the exact location of a truck depot is somewhat important for a transportation planning or transportation impact study. There are very localized traffic impact studies that people do when you have to build an access road, say to a warehouse or to a truck depot. But generally, as long as a transportation planner understands the land use pattern, that is good enough for transportation planning, because most of the existing roadways are there. But for grid planning, as we came to learn through Jonathan's group, that where exactly a truck depot is really matters in terms of the distribution system. So we took took a lot of effort to actually assemble this entirely new data set, which is a truck depot data set. To do that, and what you're seeing on this map is a depot map for the Dallas-Fort Worth area. as a requisite step for us to complete this project. In this process, we have developed this analytics procedure and data set that's derived from satellite imagery, from land use data, from property tax records, commercially available fleet databases, and point of interest maps. I'm more than happy to discuss offline why it is so difficult to obtain truck depot locations. But for now, let me just state that the truck depot location data set is a foundational step towards being able to identify potential truck charging locations moving forward. So with that, there are multiple other steps that allowed us to actually derive how much charging demand from upcoming truck electrification efforts might result at each location. So hour by hour, how many kilowatt hours might arise, and how will that manifest into power requirements given different charger choices, charger assumptions. So how do you know then, when we estimate the energy requirements, how do we know that our estimates are correct? So we did extensive validation under the DOE project. We did the validation from two sides. One is from the travel side, so travel demand. Did we capture most of the truck traffic? And on the other side is, did we capture most of the energy requirement if all vehicles become electric? And so our estimates are around within, DOE's requirements was actually 20%, within 20%. And that's typical because our estimates are bottom-up estimates, agent-based simulation. It's fairly typical for bottom-up estimates to come in within 20% of our top-down estimates. That's the typical requirement, but we actually beat that requirement by quite a lot. So on the traffic side, it's under 10%, and on the energy side, it's slightly over. And so what does it actually mean? We're really proud to show that this research project has already led to practical applications. So right now, actually, First Energy, its MET-ED territory, is using the depot map dataset that we developed and the methods that we developed through the project to estimate charging demand at these depot locations to be used in their grid planning practices. So next, let me go to passenger vehicle charging. So this project is on California, is in California, working with PG&E. This is, as the title indicates, it's focused in multifamily housing, and this has typically been a barrier to EV adoption because multifamily housing units typically have difficulty obtaining charging infrastructure. So the way we went about it is, again, starting from travel demand, how much these multifamily housing unit dwellers have to travel throughout the day, origins and destinations. If they are to electrify, how much energy would they need at what time of day? And then allow the charging demand analytics to be overlaid on the grid, onto grid assessment. So this project is still ongoing, but I wanted to share some of the intermediate results. So far we have completed the charging demand simulation for light duty for the passenger vehicles. We were able to apply our charging demand simulator for passenger vehicles to arrive at hour-by-hour energy estimates for the entire PG&E territory at a block group level. And the next step, actually, we just completed this, is to map the demand to multifamily housing units. And most recently, with a collaboration through Jonathan's group, we actually developed shovel-ready project site list, which I'll get to in the next slide. But I wanted to just point out that our simulation was able to finish for the entire state of California within just a few hours, which paves the way for day-ahead scheduling that Jonathan showed in his earlier slides. Because now you can actually test, some of the assumptions and say, okay, what if people can charge here, not there, charge at this time, not there, not that time? How would that affect their daily travel? What are the constraints? How many people can take up this respond to this type of pricing signals? How much difference can I actually observe on the load side? Again, on validation. So because passenger vehicles, there's a lot more adoption compared to trucks, we actually use backcasting as our validation method. So looking at what is our modeled, what is our model saying versus what is the actual real world observations. For that, we also did it on two sides. One is on EV registrations. What you're seeing here is our modeled EV adoption levels in the Houston region, and the actual sales numbers as the dots overlaid on the lines. And on the right, as we have observed charger utilization, which we were able to acquire for most of the public DC fast chargers. And then we calculate our estimated charging demand, and we correlate, we plot them against each other to make sure that our estimates are correct from a backcasting perspective. Because we're able to validate our approach, and now these analytics are being used in the multifamily program outreach process. As I mentioned, we have allocated the charging demand to each location. So with the analytics at the end of the day, for a utility, the important thing is to be able to identify high demand, grid-ready multifamily locations so that the team can perform targeted program outreach for multifamily properties. Just last two slides, just wanted to cover what we have achieved so far in terms of outcomes. We do have 2 peer-reviewed publications. We have talked a lot so far on the technical impacts, the actual grid impacts of transportation electrification. But I don't want to overlook the fact that with these analytics, it also allows us to go to the decade timescale that Jonathan mentioned earlier to look at emissions. And we do have an joint publication, the second one on the list here, that looks at the emissions impact of transportation electrification. On the practical side, right here in Texas, we actually were able to apply both sides of the simulations. So passenger vehicle charging demand simulation and the truck side charging demand simulation, and support a coalition of utilities to understand and estimate EV charging demand and its potential impact on the grid. So with that, I'll hand it back to Jonathan to talk about the grid side of things. Jonathan, are you able to come back online? Well, as we wait, I do see that there are three questions, so I'll go ahead and answer them in the Q&A section. Are all of the data sets open source? No, but we are we're happy to discuss with you how to get access to the data sets. What is the forecasting error here? Around 20, I think I mentioned that. Hopefully in time in the validation states, validation section, under 20% for sure. What forecasting method is used here? It's actually an agent-based Monte Carlo simulation, actually a series of Monte Carlo simulation, and I'll be happy to share detailed methods offline.
Great. Awesome. Thank you so much, Anne. Sorry about that. Zoom has a bad habit of moving the mute button around. So I was looking for it where it was before and then moved to a completely different screen, different window. So sorry for that delay, y'all. And I saw, Russell, you have a question as well that Anne can address at the end. Anne and I can both address at the end. So back to the grid side of things, I think I'll go for about 10 minutes. I'm going to start high level and then I'll get into a little bit more of the details. But then we'll go from there. So as Anne mentioned, we have two publications that we have been accepted and published. So one of them published, one of them accepted, and will be published soon. And we're currently writing 3 more journal papers from the projects that Anne mentioned: the truck charging project in Texas and the multifamily project in Northern California in the PG&E service territory. So how we model things on the grid side of things is we first start with our combined T&D models, whether that is the synthetic models I'm showing here for Texas. There's 7,000 transmission buses and about 4 million distribution nodes, I think, or it's 13 million distribution nodes. Either way, it's a massive number of distribution nodes. And so I think it's 13 million. And so we take these synthetic systems, so realistic but not real, that meaning that these data sets are completely open source, but since they don't represent an alternative version of the grid, you wouldn't and shouldn't use these for real EV integration, saying yes, we should put EV truck depots here and there, but what we can and have used them for is to validate methodology. So saying if you take scenarios, EV charging scenarios from Anne's team, and you run it through our synthetic grids, you can compare deltas, differential costs. So you can say if this is the base cost, with no EV adoption, what is the change in cost? What is the change in cost between that and 25, 50, 100% adoption? And so those numbers are more meaningful than saying put this EV charger at this specific location. For the PG&E project, we are using the real WEC grid. We have that through NDA through WEC, and we also have some publicly available PG&E load hosting capacity data that we have. Although on other proposals that we're currently working on submitting, we're partnering with some utility companies here in Texas to use real distribution system models to do EV integration studies on their footprints and provide a private report to the utility companies that will not be released to the public, detailing where in their system are good locations for EV integration and where are poor locations. So as a plug, for those people who are ISO, utility, RTO, et cetera, on the call, if you are interested in doing that and partnering with us, we'd love to partner with you. We have, I think, 3 grants we're currently applying for. So we'd love to have y'all on our team. The benefit to y'all is that you get, as part of the deliverables to y'all, so you get, like I said, you get that report on your system for what sections of the grid are good for EV and will not be good for EV. Now, granted, that's a single time snapshot, and as things evolve and change, an ongoing partnership, of course, would be great. So continuing on for the simulation, what we do is, the first thing we do is we take the EV load and we map it to the transmission or distribution systems, depending on the size of the load. And I talked a bit about that in my previous webinar. We're working on publishing a paper on the different mapping methodologies. The shortest version is there's a couple different methods. One is just grabbing the nearest transmission or distribution node or bus. Another method involves kind of creating these tessellating polygons to approximate service territories for synthetic grids if the service territory is not strictly known. So then what we do is we go in and we do combined T&D transmission and distribution co-simulation. So we have a controller that shares information back and forth between your transmission system solver, so in our case, PowerWorld, and the distribution system. In this case, we're using OpenDSS. And this is a slide from my previous webinar for those who attended both, and so you probably recognize this, but we'll go into a little bit more detail here. Apologies that it's a little bit overwhelming, but I'll trace it through with y'all. Here's this. So first you start with each distribution system. And so the distribution systems here are in green. And so if you notice, they're all solved in parallel. So you have distribution system 1 all the way up to distribution system. In our case, for the truck charging project, we looked at 1,800 feeders distribution system models. And then I think for the PG&E one, we're looking at 3,000 distribution feeders. So very large scale. So we can run we can run them all in parallel. And so that as many cores as your system has, that's how many distribution systems will be solved in parallel. You can also, the way the OpenDSS and Helix, well, the way that Helix works, which is our controller, you can parallelize it across multiple nodes. So if you have a cluster, you can solve this thing using multiple nodes. So first thing we do is we take the distribution level EV charging load from that mapping algorithms that I mentioned. We incorporate that into the power flow. So we solve the power flow in the distribution system. We'll get to how that's solved in a minute. And we send the resulting data, in this case, the substation load, the current node. Yeah, the P and the Q are sent back to the controller Helix, and then are sent over to, that information is then sent over into PowerWorld. So receive the distribution system data, and then has this simulation converged. So then if there's also an additional loop in here that shows how this is run iteratively. So you solve it, you send the data, and then if you're not within tolerance, you'll go back and rerun distribution, rerun transmission, send it back to the controller. So to avoid making it be very overly complicated, we just showed one iteration, for example. And so after the OPF and the distribution system power flow have converged, then we look at the cost analysis. So there's two different analysis methods that we use. One is assuming a firm EV load, meaning it's fixed. We're not doing any sort of load shifting or demand response. And so then you would just advance to the next time step, whether it's 15 minutes or hour, rerun the combined T&D again. Or if that node or that bus is beyond a preset LMP threshold, we have implemented some demand response modeling where you can shift a portion of the EV load, as Anne mentioned, depending on the transportation simulation, that will indicate the percentage of the EV load that is flexible based off of at the first and foremost constraint, which is moving goods and people and to their destinations. That's first and always will be the goal of transportation. But with the flexibility that is given, we can then delay some of the load and we continue that process. So if the load is delayed to the next time step, then we update the EV load on the distribution and the transmission system from the load of that hour plus the percentage of the delayed load, accounting for maximum charging rate, and continue that process. So for a transmission OPF, you would solve it. So if you wanted to implement this combined T&D in your own utility or your own university, you use your grid analysis software of choice. We use PowerWorld here, but we could use PSSC, PSLF. And so the way PowerWorld solves the OPF is using the sequential linear programming. So it linearizes so first solves an AC power flow, and then it linearizes around an operating point, and solves an LP, a linear program. Then it goes to and solves an AC power flow to assure AC convergence. And then if that AC power flow is infeasible, meaning it's got voltage violations or line limit violations, it'll relinearize and solve the OPF, solve the linear OPF again to try to correct those violations. It continues until either until the optimality gap is, until the solution differ by less than a threshold, or until the maximum number of iterations are reached. So particularly for Power World, it uses soft constraints. So it models the bus voltage and the NVA limits as soft constraints using a penalty function. So that this is in contrast to other, solution techniques where, like for example, with power models, where it'll just return infeasible. If there is no feasible solution, unless you're using unless you specify soft constraints, it treats the voltage and the line limits as hard constraints, and so therefore it returns infeasible. So the benefit of using Power World is that if you have a case where you still want a converged solution, you want to compare the magnitude of the overload for given EV charging scenarios, which is what we did, you can still have an AC solution to a case that is infeasible from an optimization perspective, meaning it has violations in the case. So this is a flowchart of what I just mentioned in the past. This is for your future reference. Those who know AC OPF will immediately recognize this flowchart, what's in the flowchart. So for the distribution side of things, and then I'll wrap up, you would use your favorite distribution system modeling software. So here at A&M, we use OpenDSS or NRI from EPE. So OpenDSS provides a unbalanced distribution system power flow. You can look at single phase feeders, do two phase or three phase feeders or laterals. So it computes the losses, the voltage, the node voltage, the current flow on the line, the complex current flow, the complex voltage, and other information. So that the complex current and voltage are used at the substation are used to calculate the P and the Q that are sent back to the transmission system for the OPF solution. So in this case, we're modeling loads and DG as either real power injections or withdrawals, or as current withdrawals. So this is just the flowchart for solving the distribution power flow. Fairly standard. You iterate every iteration. You continue to iterate, and then you look to see if there's a convergence criteria of, is the mismatch within the tolerance? If not, then continue solving. And then once you've reached that, or if you hit the number of iterations, then you end the solution. So these are some sample results for that truck charging project. We looked at some substation loads. And so some of these are individual EV loads, and so some of them can go up fairly high to like 900 kilowatts for a single depot. And some of them go higher than that once you incorporate multiple large truck charging. And then also looking at the transmission marginal cost. This is just some sample results we're going to include a lot more results. So in the previous webinar that I gave, I gave some more detailed results in table form. So feel free to go grab those slides off of our website, Smart Grid Center website. Andrea can send out a link to the attendees if you're interested with the link to those previous slides and the recording. And for this, though, I figured some visualization to be useful. So you can see how in this particular time, there's some congestion caused by EV charging in the Houston area, which causes the LMPs to increase. And interestingly, College Station has some interesting congestion too. You have a lower LMP at around 10, roughly 10, and up to $40 or $50 megawatt hour. This I think is a nighttime charging scenario because the normal LMP is around 20 or so. And then this right here kind of shows paths of overloads. Now notice it says distribution overloads. There's not a distribution line that runs all the way from Houston to Dallas. This is basically just looking at representative pieces of overloads on the system. So we have ways of visualizing that as well. The problem with being so zoomed out is you can't see specifics in the distribution system, but we have visualizations we're going to be including in our papers that show very specific what segments of the distribution system lines are overloaded, which transmission lines are overloaded, et cetera. So future work so our past work we've done co-simulation. We're currently doing we've done kind of a handoffs co-simulation where Ann's team would give us an EV charging result, and then we would do our co-simulation, what we're currently doing is we're looking at kind of bidirectional feedback, where if we shift load on the distribution and transmission side of things, then that will also rerun. There'll be some updates to the transportation side of things. So normally, for like a normal case, you wouldn't change the flow of goods or people. But say, for example, in an extreme event like Winter Storm Uri, where the grid is not able to charge electric vehicles, having that updated transportation modeling to account for the change in the available power that's even sent to the vehicle. So that's something that we're currently working on. And then our future work with our proposals we've submitted and looking for project partners is this combined transportation, transmission, and distribution co-optimization and control. And with that, we will open up for questions.
Thank you very much, Jonathan and Anne. There are some questions in the Q&A window. Russell Boyer is asking, have you done any modeling or simulation how vehicle to grid scenarios will impact the grid? For example, bidirectional?
We did actually. So the Jess and Junkyo, two of Professor Obi's former students, published a paper about VG analysis with Winter Storm Uri. That's not the primary focus of our research. As I mentioned, right now we're focusing more on just grid to vehicle, meaning, how can delaying EV charging or managed EV charging, how can that help, rather than necessarily saying, since Anne mentioned the primary goal of transportation is to move people and goods. And so why would we take power out of a vehicle in a normal situation to try to support the grid? The exception is for something like Winter Storm Uri. Could you use like your car as a microgrid to power your home so you don't, your pipes don't freeze? That's the type of questions we have and we could answer.
Next question, are there potential negative impact on the grid according to the simulation? Any information about harmonics?
No information on harmonics yet. That's why saying it's challenging, because the grid analysis spans the timescale separation. And negative impact on the grid from the managed EV charging perspective, no major ones. But as I mentioned, electric vehicles themselves do have, if uncoordinated, can cause issues with the grid, as I mentioned earlier in my presentation.
For power flow, how do you model EV cars, battery, and EV chargers? That's
an and question. For how do we model the EV cars and battery and chargers? Oh, you're on mute, Anne.
For power flow.
Yeah, sorry. So, so that is how our agent-based charging simulation model comes into play, and I think that will address the other question about what type of EV model do you find suitable for simulations. So our view is for, especially, if we want to get at least from T&D planning to demand response in that kind of time scale, you have to be able to have a rapid dynamic simulation model, but with very high spatial and temporal resolution, meaning at the scale suitable for demand response. So we are, we're looking at down to 15-minute resolution. Typically, we'll do it at hourly level, but down to the address level from a spatial side.
So for the sake of time, Andrea, I don't mind just kind of rattling off the next couple of questions, and then we can if people can email if they have questions. So the next one is, how do you combine unbalanced D subloads to present T system positive sequence load? Great question. I think right now we're just averaging the 3 phases to go to the transmission system. That's actually a subject of ongoing work and proposals, working with some professors here to better model the unbalance on the distribution system on the transmission system, but that's future work. Type of EV models, and address that. We'd love to talk more offline if you want. That's next question. So someone said they use MATLAB and OpenDSS. How do you couple network voltages and power at the interface bus? We use Helix to do that with PowerWorld and OpenDSS. We'd love to talk more offline on that one. And then last question is, are you considering currents and voltages, current and voltage violations when controlling EVs? On the transmission system, yes. So on the distribution system, not yet, because traditionally distribution systems are operated. There isn't as much visibility in the distribution system. Like you typically don't see if a line's overloaded until a fuse pops. A feeder might be a different story. So that's kind of a next step, is to say, how can we use more advanced distribution system telemetry or vehicle telemetry, or say, micro PMUs, et cetera, to be able to pull more data from the distribution system to be able to control EV charging, to not overload distribution system feeders. But great question. That is definitely ongoing work. And I see we're right at 4 o'clock.
Well, thank you very much, Jonathan, and for this comprehensive presentation, for everyone for attending. Our next webinar will be held by Dr. Roberby on using weather data application in power system modeling in September. Please watch out for the detailed announcement coming, hopefully early next week. Until then, take care and goodbye.
Bye, everybody.
Thank
Thanks
you,
for tuning in.
everyone. Bye.